What's going on, guys, and welcome to part 5 of the NanoChat from Scratch series. In this video, we will be doing the last section on the tokenizer, so that's exciting. We can actually get to the model after this. Take off my glasses, we're gonna get serious in this video. And the plan today is simple. We're gonna go through a few functions that exist in the NanoChat repository, which are necessary for performing training and evaluation, because I didn't say it, but mainly in this episode, we're going to go through the training and the evaluation of the tokenizer itself, because we've pretty much done everything already in terms of creating the tokenizer. Now we just want to evaluate it and see, like, is it performing as good as the NanoChat tokenizer? There's 2 more helper functions, and as I mentioned, we first have to train it before we evaluate it. I trained it on the, I'll show you right now actually, I trained it on the Rust BP tokenizer, and this took 48 seconds with these parameters, which we're going to keep the same. So everything that we got here, we'll compare it with what we get when we test it on our tokenizer. So we come back to tokenizer pi, and then we'll be using the SSH script that Karpathy uses. What else? We're going to go through the data set and the commons Python files as well, since those are files which we require in order to test, because we need to test on data. So with that being said, let's just get straight into it. So right now, what directory are we in? We're in the NanoChat from Scratch directory. And what I want to do is copy some files from the directory of NanoChat. So if we go one out and then another one, this should bring us into NanoChat. Okay, and the first thing we want is the train. So let me look and remember what we have here. So I think that if I get up here, it's either in scripts or NanoChat. Let's see what's in scripts. Right, so yes, we have TOKey train, and we're just going to copy it into the current, actually no, we're going to copy it into the scripts directory. And now it's in here. And let's go through this together. So there's once again the common data set, which we need to import later, but we're going to first just go through this function and describe each of the segments. So first of all, you have a description and then the 3 parameters that we care about, and the only one that we're actually going to set is the max chars. For some reason it's 10 million here, or 10 billion, but in the testing we use a 20 billion size, if I'm not mistaken, right? Sorry, 2 billion. So that's, I guess, in the interest of time, you don't want to make the set too large so that it takes a long amount of time, and it's already took 48 seconds. So we want it to happen live, then we want that to be smaller, so a fifth. Then the amount of documents that it would read, and then the vocab size. So it's interesting, like, one of these will be met before the other, right? Because either you'll first reach the maximum amount of characters or the maximum amount of documents. So I'm not sure which one actually is reached first. Like, you could just do a print statement every single time you check the if statement to see which one is scaling faster to see, but that's not really interesting. We're not going to do that. And then the text iterator is what creates the text that we train on. And this takes, what does it do? Oh yes, I was going to say, where's the data coming from? It's coming from Parquet's iter batched. So once we get through this, then I'll go through the things that we import from data in common. But essentially we get our data, and then we are always checking if we've reached the number of max documents, then we'll quit. Or if we reach the number of characters, then we'll return. In fact, I'm not sure. Okay, if the len of the documents is greater than the max number of the max number of documents, then doc text equals, yeah, we just essentially truncate it to that amount. So crop every document. Okay, it's the maximum characters per document. I thought it was the maximum number of documents, but it's the maximum characters per document. So in that case, we always have this one as the final statement. I'm not too sure what yield does. Does it tell us if I highlight it? Yeah, I'm not too familiar with that Python keyword, but that's not important. Then we train the tokenizer, we do time. We can actually change this right now to NanoChatTokenizer, and it's not even imported, so I'm not sure. Oh, it is. Okay, that's cool. So we'll just remove that because the recipe tokenizer for us is the NanoChat tokenizer. And then where were we? Right, we were here. Train for the iterator with the text iterator that we just made here. And the vocab size, which is going to be 65,336. The train time, and then print the train time. Simple stuff. Then we get the baster. This is another thing that we'll get from our comments .py, which is from the NanoChat repository. Then we save the tokenizer at the proper directory, which in this case is, actually I'll tell you guys, it's from root, it's in the cache and NanoChat. So that is the directory that is used by default for NanoChat to save tokenizers and any other logging data. Then there's a sanity check to make sure that we're actually training something that works. And then here is really a significant section of the train script. So let's just read what it says. We wish to cache a mapping from token ID to number of bytes of that token for efficient evaluation of bits per byte. Unlike the typical mean loss, this allows us to report a loss that is invariant to the vocab size of the tokenizer. And the bits per byte on the validation set is one of the primary metrics we care about to measure token compression. So the key thing here is that unlike the typical mean loss, this allows us to report a loss that is invariant of the vocab size of the tokenizer, with the typical mean loss being the sum of the loss over all of your tokens divided by the number of tokens. So mean, right? Sum of the loss divided by the number, this gives you the mean. The sum divided by the number gives you the mean, of course. And what this means is that if, for example, you have a tokenizer that has a small amount, a small vocabulary size, then it could have many tokens, which would mean that if you compare it with an analogous tokenizer that has a larger vocabulary size, the one with the larger vocabulary size might have a smaller denominator because you have less tokens for given text, since it has a better, it has more merges. And what this means is that the loss will be larger for a tokenizer that has a better amount of merges, since you just have simply less tokens for the same amount of text. But this doesn't necessarily mean that it has a poor compression ratio. So in order to kind of get rid of this token semantics, we divide by the number of bytes instead of the number of tokens. And since the number of bytes is invariant on the tokenizer, like whatever tokenizer you use, it doesn't matter. You always have the same number of bytes. Then this will give us a invariant, a measure that is invariant to the vocab size. So there you have it. How do we get this mapping from token ID to number of bytes? I'll just go through it one by one. So you first get the vocab size, since that's what we're iterating over. Right, we get the token strings, which gives us a vocab size. And then we get the set of special tokens, because in our case, special characters are not counted. They just count as 0. And then we'll get the token strings, which for every vocab ID will give us the corresponding string. So it's just tokenizer.decode the token ID for token ID in range of 65,000. And then now we initialize a empty dictionary of the bytes, which is what we are going to save here as a torch.pt file. And then now for the token string and token strings, which is the Python string representation of each token, if it's a special token, once again, we don't count it, but otherwise we'll say that the ID bytes is the length of the encoding of that string in UTF-8, which is the number of bytes that make up this token. So one example that I wrote for myself is like, if you merge the A and B characters, then each one of those is one UTF-8 byte. So like, let's say you have like the word about many times in your text, then without a doubt, AB will become a merge token. And then this will have length 2, because A is length 1 and B is length 2, and it's a merged text, so you have 1 plus 1 equals 2. And then you add this to the token bytes list. And since we're appending it, then it'll be in the correct order because we're going ID by ID from the 0th ID to the 65,335th ID. And then we make a token bytes tensor of type 32 because you can have, I'm not sure why we've chosen the data set to be 32. I assume that this is because a encoding for a character can be up to 4 bytes. If it's like an emoji, for example. And then now we just take the byte, we take the path, which is the same as the tokenizer directory. And then it's not a tokenizer, so we instead call it token_bytes.pt. If you're saving a tokenizer, then we would change this to tokenizer.pickle because we serialize them in pickle format, but that's not the case here. And then what's going on, we just save it. Okay, and then finally we will log some data such as the token bytes min, token bytes max, token bytes mean, and token bytes standard, which would say like the token bytes max is like what's the longest element in your vocabulary based on the token size, based on the number of bytes that are composed of that token. Okay, so now we have a few things. Actually, there's more things than I thought which we need. So let's just copy them one by one. So in our previous, shoot. I just lost what I wanted. I don't know how let me just see how this option works. So option, okay. As I was going to do, we now need from dataset and from comment. So if we go into NanoChat and get dataset, then we can also put that into NanoChat here. Oh, what the hell? I did a copy on copy. I hope this didn't screw up anything. It looks like it didn't. And then what else do we want? We need common. And then we'll go through these one by one, even though common is kind of trivial. Okay, so let's first look at common. These are just common utilities for NanoChat. There's a colored formatter. There's a setup default logging. There's a get base directory, which is the only one that's important to us. So this says co-locate NanoChat intermediaries with other cache data in the cache directory by default at root. So this is what we're going to use, and that's once again why it's said that it's like located here at the NanoChat directory in under cache. So we're not going to, if you do specify your own directory here in the environment, then it will use that, but otherwise it will just use the home dir. Then there's download file with lock. There's print banner of NanoChat, which I guess is used when you initialize a training run. I'm not actually sure. There's print 0. There's a bunch of compute stuff and the dummy 1db class. So none of this stuff is interesting. There is some interesting stuff in dataset.py in contrast. So let's look at that. So this file contains utilities for iterating over the Parquet files and yielding documents from it, downloading files on demand if they're not on disk. There's also another directory which we're not going to look through in this series, but since it's not actually included in the runtime, but it just details how the dataset was prepared. Yeah, so this just gets the base / pre-training dataset as a set of Parquet files. So what we have here is specifying the current pre-training dataset. For example, the number of shards if there are is up to 1,822 shards in the pre-training dataset. And then there's some helper functions here, such as one that looks into a data dir and returns the full path of all the Parquet files. What is a Parquet file actually? So it's a Apache standard. So Apache is like the open source organization which has many different standards for data storage, and it's actually stored column-wise. So you call it columnar data storage. And this is really nice because if you want to go through a subset of the columns of a data set, so let's say like you have a massive Google Sheets file and you only want like the XY columns, and there's like 100 other columns. Since it is stored column-wise, then you can just, instead of having to like slice through all the rows and grab the columns, when it's stored row-wise, you simply grab those 2 columns and you discard everything, and it's much more efficient. And there's also a bunch of compression going on too. So just know that Parquet is a really efficient way to store data. And then there's this function which is actually used in our train.py right here, where is it? Right here, to get the data that we're training on, and we import it in this line 11. So what does this do? It iterates through the data set in batches of underlying row groups for efficiency. The split can be train or val. The last parquet file will be val. So I assume everything before it is train. I'm not sure actually how it's stored. And then the start step are useful for skipping rows in distributed data parallelism. For instance, start equals ranks and step equals row size. So DDP is when you have a model copied on separate GPUs. And I think this means that you're slicing the data set. So you step on world size, which is the number of GPUs. So for instance, if you have 8 GPUs, then like GPU 1 will take every 8th row or every 8th data entry. And then GPU 2 will, with the offset of 1, take every 8th so that it's distributed across the devices. And this is why you need a step. And then the start is just the rank. So if you're on GPU 0, then you start at index 0. If you're on GPU 1, you'll start at index 1. So you have this rank offset of the number of GPUs. So it's just really simple, right? We check, are we either getting train or val? If not, then something's wrong. And then we get our paths from this file. It's really cool. And then we just go through it and grab those files. Then we have a download a single file, which just downloads a file with some backoff. I guess this means the number of attempts with the retries. If the file already exists, then you don't download it. And then there's some HTTP handling here for if the attempt fails, there's an exponential backoff, whatever that means. It backs off exponentially, I suppose. And then there's also this main function here, which is actually downloading a 100. I'm not sure what BT stands for, billion, maybe bytes. I'm not sure. It's not a billion terabytes for sure. And this is actually already done because I've downloaded the data in advance. But if you do just call the dataset.py, then it will download from a Hugging Face dataset which Karpathy made. Okay, so that's dataset. Now if we come back to train, I realized that we also will need the report .py. So let's go grab that. I think it's also in the NanoChat because that's how it's been indexed in this Python relative import. And let's see what's in report. So this is utilities for generating training report cards. More messy code than usual, we'll fix. It doesn't look like it's been fixed, but one thing worth noting is like, this is the from scratch tutorial, right? But when it comes to like utilities, report, and all of this stuff, which isn't really in the nitty gritty and the essence of the database, I'm not gonna implement that line by line with you guys because that's redundant. And even here, right, it's like 400 lines. It's like a bunch of helpers which get info, get GPU info, a lot of get methods, generate header for a training report. So I'll just give you guys a sneak peek, right? Grab these headers and this function makes those headers. Let's just go through this quickly. Like this is a template for what it looks like when you create a report. There's a slugify, which is interesting. So these are the MD files which you get generated here, right? But actually it's called like tokenizer. I'll show you guys where we have this. I think it's in tokenizer.py. Or it might not, no, it's sorry, tokenizer.train. It might or may not be here. Oh yes, okay. So, right, we call get report and log on this section. And the section is called tokenizer training. And then if we come here, I think if I just search by section, then, or let me search by slugify. Right, so we have the section and we slugify it, which means that tokenizer, there's capital letters, but that's not important. Tokenizer training becomes, as you guys see here, tokenizer dash training. And if I come back to the slugify, you'll see how that happens. It makes the text lowercase and replaces any spaces with hyphens. And these are the expected files. So only at this moment we get tokenizer evaluation and tokenizer training, but later on we'll also get these statistics from like mid training, RL, base model training, etc. And then these are metrics, but these are used for like the model evaluation itself, but not the tokenizer evaluation. A bunch of extract, the report class, which contains a bunch of logic for generating the report, and then a method for getting the report. And then a main method, which will either take generate or reset. So reset will reset the report and clear it, and then generate will just generate a new one. But reset more so kind of just establishes the time that you started training at, because even generate will overwrite and reset the previous reports. That's why I have them actually stored here, because as I mentioned, right, the cache is stored in the root directory .cache, but why do I have a cache in the NanoChat directory? It's because if I have these old reports in the standard storage directory, which is this, then when I train it with our tokenizer, then it'll be reset. And one other thing that I want, and I just realized that we need, is the PyProject.toml. So if I come here and go one directory out for the PyProject.toml, that is also going to be necessary. Let's see, where has it been? Oh, what's going on? Oh, I didn't actually specify where I want it. I want it here. Because of course we need like all of these dependencies. So actually, since I'm currently in the I spelled deactivate wrong. So I'm currently in a VNV of a parent directory. I'm going to deactivate it, and then call uvsync on this new PyProject.toml, which should make a VNV within our directory. Great. So this is already going to be set up so that we don't get a bunch of errors when I try to run the training run in a few minutes. But let's just make sure that we haven't forgotten anything. So we've done toke_train. We haven't done the last two helper functions. So let's go ahead and do that right now in the tokenizer.py. So the first one is called getTokenizer. And this is kind of similar to the method that returns a tokenizer load. Where is it? Sorry, from directory. And it's just a wrapper around from directory. So what is the purpose of this function? It loads the tokenizer from the standard location, which in this case, let me just copy paste what I have here. Loads the tokenizer from the standard location, which is cache NanoChatTokenizer, used throughout the code bases of hard-coding paths. So you can think of the from directory method as an internal method, which is used if you have the tokenizer stored somewhere else. But if you're just loading tokenizer from the standard location, then it's always going to be where you want it, essentially at the cache location. And this isn't even a method of the class itself, since we're just loading the tokenizer from a place that we know beforehand. It doesn't really depend on the class at all. But what we do need is, it has, I'm just looking at my notes, and it has from nanochat.common import getBaster, because I guess we don't have this anywhere else in our tokenizer.py. And once again, this is because we want it from the standard location. So baster equals getBaster. Very, very sophisticated code here, guys. That's a function. And then now we want to specify the tokenizer directory, which is just the os.path.join, os.path.join, the base directory, come on, with my QuickTime recording just stopped for no reason. So it may be because I'm out of storage, but let's see what happens. As I was saying, it's the base directory and the tokenizer.pickle, which we will merge together. Actually, yeah, that's the proper notation. And then we will come here and say return. Oh, sorry. It's not actually the tokenizer.pickle, right? The base directory is just this. And then we want to index on, not index, but go in the tokenizer directory. And then when we return nanochat tokenizer dot from directory of the tokenizer directory, we'll see that the from directory, oh my God, is what will go ahead and add the tokenizer.pickle, right? this is that path, right? If we did tokenize pickle, then that would be like double indexing, and it would just lead to a file error. So this function is done. And now if we come here, we have one more, which is called def get underscore token underscore bytes, which will just retrieve the token underscore bytes.pytorch PyTorch object that we made here. So this will take a device, since we are dealing with a PyTorch tensor. If we're on GPU, then we'll put it on the GPU. If we're on CPU, then we'll put it on the CPU. And then we need to import torch. And also, okay, we're gonna need to use the get baster here anyway, so I'm just gonna put this above. And then also put torch above. I don't know why in Karpathy's code base he has torch as the import as within the method itself. It seems strange. Of course, since we're only importing torch for this one method, it does make sense in that case, but since we need get base directory for both, then we should have it for both. As we should have it only once, so that we don't have it redundantly, is what I mean. So let's get underscore the base directory once again. And we're gonna need a tokenizer directory anyways, because the tokenizer, the token underscore bytes.pt is also stored in the tokenizer directory. So now that we have that, we will take the token we'll also need to get the byte path itself. Can you not do a path join on multiple string literals with this? Like, let me see. I think it will just be simpler if I do token underscore bytes.pt here, because the next line is kind of redundant. We just do another path join on the token bytes underscore pt in the original code. So let's just have a quick sanity check as that the path exists itself, the tokenizer dir. Yeet. And I think we should, just assert that. Otherwise, we will say, sorry, I always forget how asserts work. It's just here. We'll just return the token bytes not found, boom. And then if it is, then if we did find it, then we'll say with open tokenizer dir. We're reading binary since it's stored in a .pt form as f token, or we don't even need to do that. I was going to say just return torch.load. I was going to first give it a variable name and then return it, but why do that when you can just return it directly within the with statement? Okay, so what does this code do? We get the base directory, we get the tokenizer directory, and then we assert that it exists, and then we return it. So if I put the purpose here, just so that it is in the code base, sorry, not in the code base, but in the it's not a type, it's not a doc string since I'm just using regular comments, but it is here so that for posteriority it can be used for reference. So now we have these two functions implemented, the two helper functions. So let's just delete things as we go along. I did see that the pyproject.toml failed. Let's see what happens. Call to matrin. All right, so matrin is not working. This usually indicates a problem with the package to build environment. So I don't even think we need matrin. I don't know what that is. It's probably something that we need for training the model later on. So let's just remove it. Or let's remove what depends on it because it's not actually here. Oh, no, it is. It's for Rust, I think. And we don't even use Rust. So let me see if I just do that, if it will resolve itself, and we'll see if this causes errors later on. Yay! Okay, so this may shoot us in the foot. This may shoot us, how do you say it? This may cause us to shoot ourselves in the foot later on, but hopefully it doesn't. I think we just went through dataset already, right? Yes, so we can remove dataset, we can remove comments. Now we just need to import the, so let's first go back. No such file or directory. Okay, I think what I just did was unnecessary. You're in this directory that we needed to be in already. We need to now grab the tokenizer.eval, and I'll show you guys what's in there. So change this to eval, and then check that out. So this eval Python function evaluates the compression ratio of the tokenizer. So one other thing is that we'll have to change this to NanoChatTokenizer. And then also you can see that the function that we just implemented to get tokenizer is now used. So that's why we needed to implement it, since it is necessary for grabbing the tokenizer from the standard location. And I think it actually is best practice to put import torch here. So forget what I said previously, but yeah, let's have best practices imports. And then NanoChatTokenizer will replace Rust BPE tokenizer wherever it is. So I want to try something, which is to say, okay, we can't, I was going to try to rename it with F2 in a kind of more Pythonic way, but forget what I said. These are just loading the pre-trained models here. Okay, and let's go through the file now. So it starts off with just some random text that Karpathy got, one in English, one in Korean to test non-English compression, and then random piece of code, and then math. Okay, so we have that. And then there's also a section on science.